On August 15, 1977, a narrowband radio transient of extreme intensity reached Earth. It was centered near the 21-centimeter hydrogen line, the most abundant element in the universe, and a region of the radio spectrum theoretically ideal for interstellar communication. 3 days later, astronomer Jerry Eman was manually auditing line printer logs from the Ohio State University Big Ear telescope. He discovered an anomalous alphanumeric sequence, 6EQU5, and wrote the exclamation "wow" in the margin. This data table establishes the historical baseline that defined the signal for nearly 50 years. Based on 1970s processing, the peak flux density was recorded at 50 Janskis, with a frequency of 1420.40 MHz. Relying on these numbers produced a decades-long scientific impasse. Natural astrophysical models could not account for the signal's precision, while artificial models struggled to explain its physical behavior, leaving the event as an unresolved mystery. In 2025, the Arecibo WOW project bypassed historical summaries to conduct a landmark reanalysis. They recovered and digitized 1.24 terabytes of archived raw magnetic tape data, assembly logs, and the original Fortran 4 source code used to run the Big Ear systems. This digital archaeology provided the first precise characterization of the signal's parameters since 1977, providing new physical constraints on the source. As this table updates, the revised 2025 parameters emerge. The peak flux density was actually greater than or equal to 256 Janskis, a four-fold increase over historical estimates, and the corrected frequency shifted to 1420.726 MHz. These updated metrics create a strict set of constraints. Any proposed generation mechanism, whether natural or artificial, must align with these revised thresholds for energy and frequency. The signal's physical profile is no longer a matter of historical estimation. It is now defined by these specific, digitized parameters. To identify the source, we have to look at the ground-based hardware that captured it. The Big Ear was a passive drift scan instrument. It remained fixed in altitude, while relying on the Earth's sidereal rotation to sweep a 10 arc-minute listening beam across the sky. This chart maps the sequence 6EQUJ5 against time. Each character represents a unitless signal-to-noise ratio measurement, captured in 12-second bins. Together, they form a symmetrical 72-second Gaussian curve, the exact signature of a stationary point source transiting through the telescope's field of view. The Big Ear utilized two separate feed horns. As this extended timeline shows, the horns scanned the same declination coordinates, but were offset horizontally, creating a temporal delay of exactly 3 minutes between them. To remove background noise, the telescope's N50CH software subtracted the signal of one horn from the other. At the time of the WOW detection, the system was configured to calculate the absolute value of this differential. This comparison illustrates the problem. A continuous celestial source would have produced two identical peaks separated by 3 minutes. The WOW signal appeared only once. This absence of a second peak confirms the signal was hypertransient. It turned on or shut off, entirely within that narrow 3-minute window between the two feed horns. The 2025 recalibration confirms that the signal's energy was concentrated into a massive, brief event of at least 256 Janskis, placing severe constraints on the power required to generate it. The Arecibo team also identified a critical hardware error. This spectrograph shows a 100 kHz discrepancy caused by a mistuned local oscillator that the university had accidentally purchased and installed. When we apply the 2025 corrections for this hardware offset, the true barycentric frequency shifts by 320 kHz. The signal moves distinctly toward the blue end of the spectrum. This frequency shift has a specific physical consequence. It indicates a radial velocity of positive 10 kilometers per second, meaning the source was moving rapidly toward our solar system. This correction defines a source that is both energetic and moving on a specific approach vector toward Earth, narrowing the list of potential candidates. We can use these constraints to eliminate previous theories. The 2016 cometary hypothesis is ruled out by the hardware data. Comets move too slowly to bypass the dual horn's 3-minute window without being detected twice. Additionally, gas emission from comets is subject to thermal broadening, which would create a wide signal. This contradicts the hyper-narrow sub-10 kHz bandwidth of the WOW signal. A more speculative theory focuses on interstellar object 3I Atlas. In August 1977, this body was 600 astronomical units from Earth, moving on a hyperbolic trajectory. This scale illustrates the energy requirement. To produce the observed flux density from a distance of 600 AU, a transmitter would need an output of 0.5 to 2.0 gigawatts, roughly the total power of a large nuclear station. The velocity data also presents a challenge. 3I Atlas was approaching at 60 kilometers per second, yet the signal's blue shift was only 10 kilometers per second. An onboard transmitter would have to actively compensate for its own Doppler effect to match the frequency we recorded. While 3I Atlas remains a focus of research due to its unique trajectory, the energy demands and necessary frequency adjustments make it a physically strained explanation. The most robust model currently aligns with the 2025 dataset, a stellar-triggered super-radiance event, effectively an astrophysical maser flare within a cold cloud of neutral hydrogen. This requires a highly energetic trigger. A background event, such as a magnetar flare, suddenly bathes a cloud of cold interstellar hydrogen in high-energy photons. This diagram shows the reaction at the atomic level. The intense photon bath causes a sudden population inversion in the hyperfine ground states of the hydrogen atoms. As the atoms return to their ground state, they stimulate a massive, coherent cascade of radiation. This produces an exponentially amplified emission, precisely at the 21-centimeter line, reaching the 256 Jansky threshold. Because the hydrogen cloud is cold, it lacks the thermal energy to broaden the signal. The resulting emission remains locked in the hyper-narrow sub-10 kHz bandwidth, recorded by the big ear. This natural model meets every physical constraint of the reanalyzed data: the extreme flux density, the narrow bandwidth, and the 3-minute transients. The transient nature of a maser flare explains why modern recovery efforts have failed. In 2022, Breakthrough Listen used the Green Bank telescope for a targeted observation of a sun-like star near the original coordinates. These sensitive surveys, alongside observations by the Allen Telescope Array, found no evidence of an active transmitter. The region remained quiet, with no signals detected above a tiny 0.3 Jansky threshold. These targeted searches rely on the assumption that a signal is continuous. If the WOW event was a rare, transient flare, pointing a telescope at the coordinates decades after it ended will inevitably yield zero results. This has shifted the search towards stochastic repeaters, emitters that flash at irregular, non-periodic intervals. Researchers are now using Bayesian statistics to calculate optimized observation windows for these random bursts. To capture these anomalies, astronomers are building wide-field monitoring networks like laser SETI. These global stations monitor the entire sky continuously, ensuring that brief, transient events are captured in real time. By utilizing multiple independent stations, researchers can overcome the spatial and temporal limitations that prevented the Big Ear from confirming the WOW signal in 1977. The signal's latency lies in identifying a rare astrophysical process that provides a new template for future transient searches. Whether the 1977 event was a unique natural flare or a deliberate beacon, it has redefined how we monitor the deep cosmos.